So I thought as I'm here, I can as well present the first part of the talk. Yeah, what is a rubble pile asteroid? We heard a bit about this before. So you've seen this famous plot with the rotation rate, with the plot over the radius of asteroids known today. And you see this cutoff there at a period of 2.2 hours. So this indicates that all or most asteroids larger than 120 meters are actually bound mainly by gravitation and only very weak cohesion. So, and additionally we have high macroporosities and the collisional history of all asteroids basically, telling us that these are leftovers of collisional evolution. So, and as well, the direct observations of Itokawa. So the evidence is there that most of these asteroids are rubble piles, or at least gravitational aggregates. But the question remains, how do they actually look in the inside? So are they, we know they have macroporosity, but how is this macroporosity distributed? Is it in lots of small voids, or is it in some big voids? We don't know at this point. So there was, for example, here on this image there, it's asteroid Steins, which was imaged by Osiris on the Rosetta mission. And so there are only indirect methods nowadays to infer the actual structure of a rubble pile asteroid. So on asteroid Steins, I did a study once where I could link the impact crater you see on the southern pole to the to these series of pit-like structures, and it shows that actually for Steins, if we have like more large-scale voids in the interior of this asteroid, then this container could be linked to this impact event. So using impact simulations nowadays, we can actually kind of infer the interior of asteroids. But to actually, well, there should be a video now. It doesn't seem to be there. Sorry for this. No video. So, yeah, this is basically a little bit how this project came together. I met Sampsa Pursiainen and Mika from Tampere, and they were developing a technology based on medical imaging, the computed tomography, and wanted to apply it on asteroids to detect the interior of asteroids. So they showed that within a body like this, they can reconstruct these black voids you see there using only sparse measurements with the radar instrument. So one important point here is that the more measurements you have, the better. So and you need a penetrating wave to actually do this accurately. So from this, basically using a twin configuration with a radar instrument is the optimum to really detect the interior of a rubble pile asteroid. So, and then I give over.
Yeah, just briefly we'll talk about the mission concept, how to get to the asteroid, and talking about the targets. I guess like after all these talks, the biggest problem is not to be stuck in a traffic jam on the way to the asteroid, but yeah, there's of course other challenges too. First, let's talk about our instrument. As Jakob said, it's a radar. We choose a 20 megahertz radar. That's kind of the optimum we can use in space because yeah, there's the one limit which is through the background noises in space, but there's also like thermal noises, which make 20 megahertz the optimal choice. And this frequency allows us more or less to penetrate through a 200-meter asteroid, which is sufficient because it allows us to completely scan an asteroid, which should be a rubble size. 20 megahertz makes it necessary to have a 7.5 meter antenna, which is huge but not possible for a 6-unit CubeSat. Yeah, the radar itself is that frequency radar, which goes to at least 265 lines, and what we have from efficiency, we need 40 watts of input power, and like we get around 10 watts of output power. We need a twin configuration because the penetrating wave is really important for the entire concept to do the tomography. Those two CubeSats will have the same instrument basically. So the receiving and the sending radar is the same configuration. So the twin configuration is also like kind of a backup. So even with a failure of one satellite, we can analyze the satellite not in that quality, but at least yeah, it's feasible. Or like if one yeah, it's partly broken, you can switch like who's sending, who's receiving. Yeah, the technology level is around 4 to 5 because the radar is basically taken from like an older ESA study. So actually, as it's a low frequency radar which is based on other concepts, we're like kind of confident that the development is not too complex. For the tomography, we need like an orbit of 5 to 7 kilometers. Actually, one orbit is sufficient. This is with the assumption that the spin of the asteroid is not parallel to the orbit axis we have with the orbiter. So basically, we take around 10 to 50,000 measurement points, and we have a total data amount between 100 and 500 MBs, which gives us eventually, with the twin configuration, a resolution around about 7 to 10 meters. Actually, more satellites increase this accuracy, more data points just slightly increase the quality of the measurement. There is like, let's say, like kind of a dual use. The same radar we use anyhow, it can also be used for just scanning the surrounding during the flight mode. So yeah, with 40 watts of input power, we can detect 150 meter asteroids in a distance of 1,000 kilometers. That's not much. Actually, it's quite unlikely that we see anything on the flight. Maybe it's more likely on the Lagrange point. But anyhow, as the same instrument without any changes can do that, the question is why wouldn't you just yeah, do this during the cruise phase? Yeah, let's talk about the target. That's just a plot of near-Earth asteroids approaching like between 2019 and 22. We are limited in our selection because we want to have minimum 200 meters of diameter, and we want to have the closest approach around 20 unit distances to not have too much trouble with the data transmission. I think I skipped this slide. Yeah. I broken that. Okay. Okay. Yeah. This is just the statistic of the discovery rate, or like which can be seen that like this year 500 new near-Earth asteroids have been discovered. So actually, new targets are constantly coming up. of course, the perfect target is not available yet. Just a video version. I'm sorry. Anyhow, like the most promising candidate is for us 2017.A.3.4, which has a relative velocity of 3.6 meters per second, and is between like 180 and 410 meters in size. We had a nice talk about how to get to Asteroid. Actually, we don't have yet the probability to do a complete analyze like how to get there. So we just did a rough estimate how to get to Asteroid. So our first idea was obviously also like taking a ride with an Asteroid mission. So we also did an analyze for 3-unit version. The 3-unit version doesn't need the transmitter for the radar, it just needs to receive. So whenever there's like any mission going to the radar, we could simply put this mission in a 3-unit CubeSat and do the same which we would do with 2 6-unit CubeSats. The second part was same which was presented before it, kind of going to a lunar escape orbit. I mean, there's been much said about the space launch system, which is booked out, I guess. But there's also like companies like SpaceX or Origin announcing it. We talked to part-time scientists, which is a German company, flying to the moon probably 2 times in a row, and also offered to take CubeSat to an escape temperature. And combining this with an electric propulsion system, which should be feasible to reach asteroids which have a delta-V of around 40 meters per second. This number is based on a study of Landis from JPL, basically. Like he analyzed the capability of going to an asteroid using SLS, basically, and he calculated that basically you get, in the worst case scenario, 1.6 kilometers per second delta-V, and depending on the electric propulsion system you have, if it's not the worst case scenario, you can reach asteroids around 4 kilometers per second, which was a delta-V of 4 kilometers per second. The third version is actually not taking your own rocket. That sounds like a little bit expensive, but new launcher concepts are coming up, and basically the costs of a ground station for 2 years checking in regular manners where your spaceship is, your CubeSat, doing the orbit correction, it might be more expensive to actually purchase a rocket, which is on the magnitude of 5 or 10 million euros. So a direct orbit installation, which is only like 2 months, might be more cost efficient basically than flying 2 years with a CubeSat, which needs to be permanently babysitted by some ground station. We took the electric propulsion version as kind of the worst case scenario, because that drives the need of occupying 3 units of the 6-unit CubeSats. It's around 3 kilos. We're thinking about how to optimize it, and actually, like we took a Buzig Bit 3 thruster as a reference, and with the highest power available, we can get like the 3-unit CubeSats on like this different weights to the reference delta-V. So for us, it's around 2.5 kilometers per second, which we need. So roughly, we should stay below 30 kilos. So that was like our design restraint. We just took like the off-the-shelf components we got, and roundabout with margins, we reached this 13.5 kilograms. So from roughly what we did, we used proven mathematical models from like a different field, like tomography basically from medical applications. we roughly estimated whether it's possible to get a 6-unit satellite with a 1 unit, 1 kilo instrument to an asteroid. And yeah, we would be able to do with this basic widget, it would be very important for planetary defense, because if you want to deflect something, you might want to know if it's like going to ash if you, or if it's like a solid body. So yeah, I guess it's a really important case for science, but also for planetary.
We have time for questions.
Very interesting talk, thanks. So just to ask you a little about the instrument, you mentioned it was 2 times 3.75 meters out there. Have you looked into any technology development you would need to do for that?
Yeah,
it's quite a long distance for a CubeSat.
Yeah, we have actually 3 approaches. One is flat proven by Philae, more or less. There we didn't use an antenna, but a mercury meter, which was deployed by Philae to the ground by just, like it was rolled, and yeah, just put out. And it was bended slightly, you know, this metal things. It was bended slightly,
Yes.
so with that it gained a lot of stability. So, and by that you could easily deploy a 3 meter, 4 meter antenna to both sides. But we're also thinking about just wrapping it around the CubeSat and releasing it. Yeah. So basically it's based on this measurement line, and I take that's the knowledge.
And you mentioned the mass and the power, but not the size, but what would be the internal volume
Of the instrument?
of the instrument?
Yeah, it's 1 unit. It's 1 unit and 1.3.
Any other questions? In that case, let's thank our speakers.